And we're back. This is going to be lecture 7.3 for Mr. Allen's chemistry class. We're talking about bonding in metals. So the objectives for this are going to be the following. Students will recall the properties of metals from the last chapter. Other objective will be students will identify the characteristics of metallic bonding. And students will recognize the compositions of selected alloys. So, a real quick review. What are the general properties of metals? Well, they are blank, which means they can be pounded into sheets. So that is they are malleable. They can be pounded into sheets. They are ductile, so they can be drawn into wires. They have relatively high melting and boiling points. And they are good conductors of heat and electricity. So, why do metals have these properties? And this is actually something I've always wondered, and I'd always wondered until I began teaching chemistry, when I learned about metallic properties. Because of the bonding processes that occur in metals, they can be malleable and ductile. What happens with metals is what's called, creatively enough, metallic bonding. Metals are made of closely packed positive metallic ions within a band or sea of valence electrons. Now, the valence electrons are mobile, which provide the conductive properties of metal. That means that they don't stick around with their host nucleus. That they travel in between all the nucleuses of all the other metals, and all of the nuclei and all of the electrons are kind of just in a gobbledygook together, and that's what makes our metals. Now, metals are malleable and ductile, okay, because the positive metallic ions have the ability to slide past each other when a force is applied to the metal. This is because the valence electrons aren't in fixed positions. So, the valence electrons aren't in fixed positions, and so here's a diagram of what this looks like, if we can leave it there. When you apply a force, let's see if I can make this a little bigger here. When you apply a force to a metal, you start pushing on the metal cations in the midst of all of the electrons around them. Well, that pushes the cations, but they can move past each other because they have this buffer of electrons around them. And that's why a metal, we can pound it and hit it into wires, and we can make, we can bend it and do this stuff because they're not in a rigid arrangement. Whereas with an ionic compound over here, we have positive ions and negative ions, and they are very rigidly and very strictly lined up. And so if we apply a force, we're going to push this negative guy to get close to that negative guy, and this positive to get close to that positive, and that negative to get close to the negative that'd be down here. And when they get close, there's a very strong repulsion between the negatives and the positives, and that actually causes that ionic crystal to shatter. That's what makes the crystal shatter. So metals have the ability to pass by each other without losing its integrity, where if you do this to an ionic compound, it shatters them, and that's why we have the ability to deal with metals like this. Now, when we add energy to metals in this way, or in any kind of way, it is absorbed in two different ways. The first one is that the positive metallic ions increase in their ion vibration. They start wiggling more and more, and they get excited. They start sitting in place. It's kind of like, they start wiggling because they're filled with energy. It's like a 5-year-old that's just had eaten all of their Halloween candy. Then, you have valence electrons. They increase in their movement, but the electrons are not they're not stuck to their cations, and so they can move independently of metals. But this is the reason why metals have high melting and boiling points, because there's two different ways for the metal to absorb the energy, which means that it's going to take more energy for both of them to start separating each other. Now, metals tend to form crystalline structures, but we're not going to go into detail on how they arrange the packing on that. Um, right, there's a cool video I may have already shown you about samurai swords and how the metal is made for them. That really goes into good detail about how metals are arranged. And the interesting thing about that video is uh, samurai swords really are not just, they're not made out of an elemental metal. They're made out of steel. And steel is an alloy. Now, alloys are mixtures of elements that are usually metals that have metallic properties. So these alloys are very important because they frequently have properties that are superior to their individual elements. For example, they're frequently stronger and more corrosion resistant, and they have higher melting and boiling points, and are still more lightweight than their individual elements. The alloys are also used in sporting equipment like baseball bats and bicycles and golf clubs, or they have, alumina alloy and titanium alloy equipment. They're used in surgical steel, aircraft parts, drill bits, and many of the metals we use in everyday processes. So we have some examples. One of them is bronze, which is usually 88% copper and 12% tin, and that is used in sculptures, as well as other things that used to be used. That used to be the warfare metal. Um, right. So, anyways, bronze has been used. Bronze is one of the original alloys from way back in the day. The fact that there's actually a Bronze Age, and bronze was used for weapons because it was a stronger metal than just the copper and the tin that go into it. Okay, but then we moved on from there to make brass, uh, and brass is used in musical instruments, home furnishings, and it looks very much like gold. And so brass was discovered to make things look pretty without actually having to be very expensive. Then we have other things. There's silver and copper. Okay, this is sterling silver, where it's 92.5% silver and 7.5% copper, and that's used for silverware and silver jewelry and so on. Okay, and that brings us to gold alloys. 24 karat is pure gold, so everything else is a fraction of 24 karat, which means that 14 karat gold would then be 14 24ths gold, or 50.5%. 18 karat gold would be 18 over 24, or 3/4 gold, and that would be 75%. 10 karat gold is 10/24, which would be 41.5% gold. That's where you'll find, Jory, most wedding bands and that sort of thing. If they're going to be gold, they're going to be in this range because they are harder and you want them to last longer. And so if you get them caught in something, or they'll take a beating. If you ever wanted to see a well beaten up gold ring, I can show you guys my wedding ring, and it's pretty well bumped up. Okay, now if you have somebody that wants to give you a gold and say, oh yeah, it's yellow gold. That is gold mixed with copper and silver, and it still has a yellowish color to it, but it's really not the same thing, and you're not getting a whole lot of gold there. And then if somebody brags out of being white gold, well, that's gold with copper and nickel, and now you're really talking about someone who's trying to pull one over on you. So ladies, it's not just about, if you want it, then you better put a ring on it. It's the kind of ring also, so make sure you guys not cheapskates. Which brings us to steel alloys, okay, which is steel alloys, which is iron mixed with carbon. And this is what our swords got made out of, and this is where we really started getting our heavy weaponry and our solid, really strong, flexible metals. There's mild steel, which is about 0.2% carbon, and that is used in nails, and usually that's just iron with a little bit of carbon, and so it's a little bit stronger than usual, and so it won't bend as much, but it's still it's still a pretty malleable substance. Medium steel, that is what's used in structural beams of buildings. Steel is an excellent use of building material because it is flexible and it allows uh, building material. It allows taller buildings. Steel has allowed us to build taller buildings um, that can withstand things like earthquakes and high winds and hurricanes uh, because of their flexibility. If they were not flexible, if they were too brittle, they would break right off and buildings would snap, skyscrapers would snap. The steel in buildings is what makes them as safe as they are. And then we get to high carbon steel. And this is where we use drill bits and cutlery and the aforementioned samurai swords. Now, we have other common alloys that are illustrated on table 7.3 in your book. And, those are all also common uses for mixtures of metal. So now what we're going to do is we're going to take our quiz. So let's jump to the back. And the valence electrons of a metal can be modeled as how? A body-centered cube, octets of electrons, a rigid array of electrons, or a sea of electrons. And the correct answer is of electrons. Our valence electrons are what hold our cations in this fluctuating sea of electrons. Okay, next question. Question number 2. In most metals, the atoms are A, free to move from one part of the metal to another, B, arranged in a compact and orderly pattern, C, placed at irregular locations, or D, randomly distributed. Okay, the correct answer is B, arranged in a compact and orderly pattern. They have this crystalline structure that's usually pretty dense and compact. Okay, but if you hammer it, you can alter that pattern. And finally, alloys are important because they are A, pure substances, are the ores from which metals can be refined, C, can have properties superior to those of their components, or D, are produced by the combustion of metals. We just spent a fair amount of time talking about this. The correct answer is C, they can have properties superior to those of their components. That is it for section 7.3. I encourage you to go on to the next video, which will be 8.1, and we'll see you guys next time.